Okay, so as I mentioned in the email, I sent it out like 20 minutes ago. Just basically saying that if you like to print out the notes ahead of time, you probably printed out chapter 2 and thought, this is nice and short. And it is. Chapter 3, we're probably going to get to that in the second hour. Um, so Tro does a very odd organization of chapters 2 and 3, in my opinion, for what it's worth. If you remember intro chem, doing mass to moles to atoms or molecules and doing those types of calculations, instead of just presenting it at one time, Tro in chapter 2 presents atoms, mass, moles, atoms. So just dealing with elements. And then he does the same calculations for compounds in chapter 3. And to me, that just seems odd. It's the same type of calculation. I'm not sure why they're separated. So I kind of reorganize things a little bit, not to be confusing, but the notes are gonna follow the chapter 2 book, right? And then the notes are gonna follow the chapter 3 in the book. If you have any questions about it, let me know. I tried to be pretty clear about how it's organized, but that's why if you look, there's just one folder for chapters 2 and 3, and it's sort of combined into one unit. Okay, so with that being said, I'm gonna go ahead and get started with chapter 2. All right, so what I love about chemistry, and I have to admit, it took me a little while to find the love for this, is that it is part foreign language and mostly a lot of math. So the math part I love. The foreign language part, a little bit harder for me. Just because I don't like memorizing things. I like to just kind of figure things out. So if you think about the language of chemistry, our alphabet is our elements, right? Those are the building blocks of all of our words and all of our sentences. So that we first have to start there. We have to learn our alphabet. And as I mentioned on Tuesday last week, when we look at our periodic table, the one that I have posted for you in my courses, this is the same one you'll have on all of your exams. So what you'll notice is, remember, some of these elements, the name is there. Scandium, which you might expect was named for Scandinavia, right? So there are elements where the name is there, and that means you do not need to memorize those. If there's an element though where the name is not there, that you need to make sure you remember for test 1. So you'll have this exact same periodic table for all of your exams. So just know that if I say, okay, you've got 100 grams of iron, then you're going to have to know, okay, iron means Fe. And I'm going to go and look for all the information I need regarding Fe. So this is one way to practice kind of quizzing yourself on the element names and symbols is by looking at your periodic table, just going through it. Anything that doesn't have a name, make sure, yep, see, there we go. Make sure that you know how to name that element. Then I also put a Quizlet. I made a Quizlet that's posted in my courses. So it's just like online virtual flashcards to help you memorize your element names and symbols. Personally, for me, I'm somebody that I learn best by writing it down. So for me, if I go through, this is probably what I would do, is I would go through my periodic table and I would go through all of the elements. And if I got to an element where I'm like, not 100%, then I would probably take that element and write it down a few times. And, write the symbol, write the name, write the symbol, write the name. And they say if you do it 6 times, you've got it. I don't know. For some, it might be more, might be less. Maybe depends on the day for me and how much sleep I've had. But that's probably what I would do. Some of these, right, they're easy: hydrogen, magnesium, calcium. But just make sure you have those element names and symbols memorized for the first exam. I will say, just from experience, magnesium, Mg, manganese, Mn. So magnesium, M, skip the A, go to G, magnesium. M, skip the A, go to N, manganese. That's one way to do it. The other two that get kind of swapped around are silver and gold. So if you knew that Au comes from aurum, which means shining dawn, and then you'd be like, oh, that makes sense that that's gold. That's helpful. Argentum, you know, there's nothing really helpful there. But anyway, those are the classical names. You do not need to know the classical names, just Ag, silver, Au is gold. The other two that kind of cause trouble, SB is antimony. It's not one that we typically use a lot. So sometimes students will just forget it, and I can see why. PB, lead, and then sometimes iron and lead get mixed. But anyway, I always remembered PB from plumbum, and I think plumbing, and then the Roman aqueducts, and they used lead, and that wasn't such a great idea. But anyway, there's little things here to help you remember, but make sure you've got those element names remembered for the first test. Okay, so the first thing is law of definite proportions, law of multiple proportions. We kind of talked about this in our first Zoom session that if it's a molecule of water, it's always H2O. It's not H2O2, it's not H3O, it's always H2O. That's your definite proportion. And then multiple proportion is that two or more elements can combine in different ratios to make different compounds. And if you remember on Tuesday, we used H2O water and H2O2, hydrogen peroxide. Another example would be carbon monoxide and carbon dioxide. So the next thing is our atomic model. And if you remember on Monday or Tuesday, sorry, I had mentioned that the original atomic model that we had is not the same one that we have now. So originally, there was some understanding of these subatomic particles. We have three protons, which I always abbreviate P with a plus sign because they're positively charged particles. Then neutrons, N with a 0 because they're neutral, makes it easy to remember. Neutrons are neutral. And then electrons to balance out the charge, right? These are our negatively charged particles. So I usually abbreviate those E with a negative sign. And if you think about it, this would make sense. If we know that positives and negatives attract, the original model of atomic structure was, okay, let's take a positive particle next to a negative, next to a positive, next to a negative. And that kind of makes sense. That would hold everything together. And that was called the raisin pudding or bread pudding model. And so that sort of makes sense that you're alternating these charges. So that's obviously going to hold everything together pretty well. And then Rutherford came along and he did some experimentation and he actually found out this was not the correct model, that instead all of the positive charge in the atom is right in the center and all the negative charge is outside of that center. And that's called the nuclear atom, right? Because it has a nucleus. And so that is our model of the atom that seems to be holding true. Now, we only have 3 subatomic particles that we have to learn. At last check, there is in fact 17 subatomic particles. So I always kind of joke and say these 3 are the chemistry ones, and then the other 14 are like physics and theoretical chem, but that's not really true. But anyway, these are the only 3 we have to know. All right, so Dalton came along in the early 1800s. And first part of his atomic theory is actually very ancient. It was developed centuries before him. And it's just that all matter has this tiniest indivisible unit. And the word for that is atomos. It's a Greek word. And so that became atoms. So all matter is composed of atoms. This is the building block of all of our matter. We talked about that on Tuesday. All atoms of a given element, like iron, will have similar mass and similar properties. But atoms of a different element like lead will be different. So that makes sense. There is some exceptions here that we didn't know about quite yet when Dalton was making his theory. But the idea is that all atoms of lead look like all other atoms of lead. All atoms of iron look different than lead, but they look like all other atoms of iron. So there's something specific about their structure. Compounds are formed when atoms of different elements bond together, right? And again, in those fixed proportions, like water is always H2O. And then a chemical reaction involves rearrangement of atoms, right? That bonds are broken and new bonds are formed, and that is a chemical change. So we talked about that in lab today. And atoms cannot be created or destroyed in a chemical reaction. So when we write our chemical equations in the coming weeks, we have to make sure that if we have 2 magnesiums on one side, on the reactant side, we have to have 2 on the product side, right? So we'll be following that law of conservation of mass when we get there. Okay, so going back to the nuclear model, when you have your atomic structure, right, the center of that, there we go. I put that in the wrong place. Let's go back over here. All right, so the nuclear model is your center of your atom is the nucleus, the nuclear model, right? In that nucleus, we have our positives and our neutrals. So our protons and our neutrons are in the nucleus. And then outside the nucleus, something we're going to look at much more when we get there is where we have all of our electrons. So the organization of the electrons is going to come later. We're not going to worry about that just yet. But this is our nuclear model. All the positive is in the center, all the negative is outside of that center. And then also with those positive particles is our neutral neutrons. All right, so protons, P with a plus sign, neutrons, N with a 0 because they're neutral. And then balancing out the charge, the electrons are negative. So +1, -1, protons and electrons, those charges will cancel out. And what's important is if we're talking about an atomic structure, right? An atom by definition is neutral. And so what that means is your number of positive protons, this is going to be fun today. Your positive protons is equal to your negative electrons. So if I have an atom with 12 protons, I have an atom with 12 electrons. If it's 20 protons, it's 20 electrons. So atoms by definition are neutral. When that proton and electron count is no longer equal, then that is not an atom, that's called an ion. So we'll get to that later. All right, so when I look at my 3 subatomic particles, the protons and the neutrons are your heavy particles. And by heavy, we mean times 10 to the negative 24 grams apiece. Obviously not very heavy, but they are 2,000 times heavier than an electron. So when we're looking at the mass of an atom, over 99.9% of that mass comes from those protons and neutrons, the heavy particles that are in the nucleus. So when you look at your atom, the mass of the atom, most of it is right here in the nucleus. Little bit kind of insignificant in comparison is the mass of the electrons. All right. Okay, positives, protons, negative electrons, neutral neutrons, and then the 2 heavy particles are in the center, the nucleus, the protons and the neutrons, and the electrons are outside of that. So that's our nuclear model. And that is our current model. All right. Now, when we go to our periodic table, and I had mentioned you may want to print one out for today. If not, don't worry about it. You can get it just by writing it down on your notes. But what we're going to look at, and this is why I love this periodic table, is it's just very simple. We have 2 numbers for each element. So it's going to make it really easy. So I'm going to take Cr, chromium, which is from chroma, meaning colored, because chromium has a lot of really beautifully colored compounds. I'm just going to rewrite it up here. So if I look at my atomic number on top, the 24, and then on the bottom, I've got 51.996. I'm going to talk more about that in just a second. Let's talk about the number on top first. All right, the number on top, this is called your atomic number. It is element specific. If you notice, every element has its own unique atomic number. And this atomic number tells us the number of protons that are in the nucleus. So I know, going back to Dalton's theory, that every atom of chromium has 24 protons in the nucleus. If I'm looking at nickel, that number is now 28. So remember what we were talking about? All atoms of chromium look the same. All atoms of nickel are different than chromium, but all atoms of nickel look the same. That's the idea. So in terms of the atomic structure, I know that every atom of chromium has 24 protons in the nucleus. And I know if we're talking about nickel, it's going to be 28 protons in the nucleus. So that's the atomic number, element specific. Now, underneath that, you have your mass numbers, right? And the mass number are the 2 heavy particles. So, right, because that's what makes up your mass. So that is your number of protons added to your number of neutrons. Now, if you notice, looking at your periodic table, a lot of times these numbers are not whole numbers. And you sit there and you kind of think, well, you can't have 0.5 neutrons, right? That doesn't work. It's either a neutron or it's not. So how do you get these numbers that are not whole numbers if you're just adding up these particles? And this number is from what's called a weighted average. And we'll understand that more in just a little bit, of all of the isotopes of that element. So this is where Dalton's theory failed, right? He said that all atoms of chromium look exactly the same. And that's not quite right, but we didn't know neutrons yet at the time, so we can forgive him. What happens is that there are different versions of chromium. Now, one thing that all of those atoms of chromium have in common is that 24 protons in the nucleus. That always is true. But the number of neutrons in the nucleus, it turns out, that can be variable. And so if I have a sample of chromium, there are those different versions of chromium, and those are called the isotopes of chromium. And together, the weighted average is where we get this 51.9961. Now, some elements have 3 isotopes, some have 7, right? There's no way to predict that. And we don't need to know that anyway, which is good. Some only have 2. It just depends. But those isotopes, the weighted average of those mass numbers, that's where this mass number is coming from. And that's why it's not a whole number. So if we're going to try to find the number of protons in an atom, that's easy. We just use the atomic number. So let's say I ask you, okay, how many protons are in a silver atom? Okay, then you'd say, okay, well, I know silver is Ag, and I know then that has to be 47 protons. If I ask you how many neutrons, what we're going to do to get the number of neutrons is we're going to take the mass number, which is the protons and neutrons combined, and we're going to subtract the atomic number, which is the number of protons. So, right, we take protons and neutrons, subtract the protons, and that'll give us our number of neutrons. All right, so proton number, easy. That's just for write the atomic number. The neutrons we're going to get by subtracting the mass number minus the atomic number. And remember, if it is an atom, which is what we're going to deal with for now, your number of protons and your number of electrons have to be equal because positives and negatives have to cancel out to go to 0 because atoms by definition are neutral. All right. So when I look at chromium's mass number, if I ask you how many neutrons are in an atom of chromium, if I don't specify, then I'm going to want you to take this mass number and round it to the nearest whole number, right? Because again, you can't have 0.9961 neutrons. You either have 1 or you have 0, right? They come as whole particles. So if I don't specify the certain isotope's mass number, you would take this mass number and round it to the whole number, the nearest whole number. So like 51.9961 would round to 52. All right, so that's what we're going to start practicing. Now, if I go back to the notes really quick, all of that's right here for you, right? Your protons is equal to your atomic number. Neutrons take the difference, mass number minus atomic number. And your electrons are equal to your protons if it's an atom, because atoms are neutral. All right. Then I also talk about the isotopes, iso meaning the same. So what's happening in the isotope is you have the same number of protons, right? Which means it's the same element, but you have a different number of neutrons. And again, Dalton's theory couldn't capture that because we didn't know what neutrons were yet. All right. Now, if electrons have come or gone, right, and we now no longer have an equal amount of protons and electrons, we now have a charged atom, and that is called an ion. All right. Okay. So let's look at a new way of doing this isotope notation. And I have to say, when I first learned this as a student, I thought, who made this up? This is kind of a strange way to do it. But you have your element symbol. So I just put E. And then you have these A and Z numbers right here. Okay. So here's where it gets confusing. So first, let's look at 10. All right. So
up, kid?
sorry, go ahead.
Yes.
Any questions for me?
Oh, okay, just refocus. Your thing was really unfocused. You couldn't read anything. It's
Yeah.
better.
Okay. Yeah. The document camera is not perfect, and it does that. It'll kind of zoom out and zoom back in. And anyway, it just takes a little second. But any other questions while I'm here? Okay. All right. So going back to this new way of writing isotope notation. So first we're looking at 10, which is from Stanham, which I said, remember, do not worry about the classical name. All I need you to know is 10 has a symbol of SN. All right. So what I'm going to do is I'm going to write the element symbol, and then we're going to use this isotope notation. A, and this is where I thought this was silly, A is the mass number and Z is the atomic number. Why wouldn't A be the atomic number? But whatever, I didn't make the rules. So A is the mass number, Z is the atomic number. So that was my first thing about this, where I thought, well, that's kind of strange. The other thing I thought was strange about this is when we look at our periodic table, most of them are this way, where the atomic number is on the top and the mass number is on the bottom. But in this notation, it's flipped. It wants the mass number on the top and the atomic number on the bottom. So there's another problem with it. And then on top of it, if I know the element symbol, the atomic number is never in question. So I don't really know why I have to write that down anyway. All right, so let me go to my periodic table and show you what I mean. So 10 is over here. It's below carbon. It's in the carbon family. So there's carbon, silicon, germanium, and there's 10. It's number 50. There's the atomic number. So what I'm going to do is I'm going to rewrite what I have on my periodic table and then show you how we're going to put it in isotope notation. So I've got the atomic number on top, 50, and then the mass number on the bottom, 118.710. So there's my mass number. Okay, so using this isotope notation, what we're going to do is we're going to change the place of the atomic number, right? The atomic number, instead of being on the top, is now going to be on the bottom, right? And again, I didn't make the rules, right? That's whoever did this, these were their rules. Now, the other thing that's different is, like we talked about, that mass number is a weighted average of all of the naturally occurring isotopes of 10. Now, we are looking at specifically in this specific example, we want to have 66 neutrons. So we are looking specifically at that isotope of 10 with 66 neutrons. So what that tells me is the mass number, it's not going to be 118.710. What I'm going to do to find the mass number is I'm going to take my number of protons and I'm going to add it to my number of neutrons, right? Because those are the two heavy particles. And that makes up the mass number. That makes sense. Mass number is the two heavy particles. So your mass number for a specific isotope is always equal to your number of positive protons and your neutral neutrons that would reside in the nucleus. So if I add these together, I get 116 heavy, right, in quotes, heavy particles. Not very heavy, but 2,000 times heavier than an electron. So that is the mass number that we're going to use for this specific isotope. Remember the 118.71, that comes from a weighted average of all of the isotopes of 10. So if 116 is one of those isotope mass numbers, you can imagine 120, 121 also probably in there to get this weighted average. All right. So again, what I thought was a little strange about this particular isotope notation is, number one, it flips. Atomic number on the top on the periodic table goes to the bottom. And then the other thing is that if I know it's 10, I know it's a 50, because if I change the atomic number, it's no longer 10. So that always seemed a little redundant. The isotope notation I prefer to use is where you write the name of the element, and then after that, you provide the specific mass number. So this isotope notation, which is the SN with the mass number and the atomic number, instead you could write it as your element name with just the mass number, because the mass number is really the only thing that's variable. Again, the atomic number is never going to change. So if we do that same thing or similar with this isotope here, I've got 52 over 24, right? And then Cr, which we talked about, was chromium. All right. And then this would be the other way that I would write that same isotope information, right? Remember, chromium, the atomic number was 24. And the only thing that can vary is that mass number. All right. In this case, we're looking at specifically the mass number 52. So let's get protons, electrons, and neutrons for the atom of chromium 52, mass number of 52. Okay. So first thing is, when I go to my periodic table, that atomic number, 24, same as the one that's here. Okay, so that is our number of protons. So your number of protons is equal to your atomic number, which is equal to 24. All right, then the next thing that we're looking for is the number of electrons. All right, so if you remember that protons are positives and electrons are, that's frustrating. The protons are positives, the electrons are negative. Atoms, again, neutral. So whenever it's asking you, oh, question in the chat, are both forms going to be on the test? I have to tell you, I like this version better. But you will see the other version, like in the dynamic study guide. And you might see it like on the quizzes, but I like this version much better, where I give the element name and then the mass number. But I have to make sure you understand what this version also is telling you. Okay, it's a good question. Okay, so back to where we were. If it's telling you that you have an atom, that's important because then you know it is neutral. If it says an ion, which we'll talk about later, that will change some things. But if it's an atom, it's neutral. And then that means that your number of electrons is equal to your number of protons. But again, that's only true for an atom. All right. And so then we would also have 24 electrons. So we've got 24 protons, 24 electrons. Now let's figure out our number of neutrons. So as we practiced before, we're going to take that mass number and minus the atomic number to get our number of neutrons. We have a total of 52 heavy particles, right? That is our isotope mass number, 52. Then we minus out the atomic number of 24. So remember the 52 is the protons and the neutrons, right? So that's both of those particles. And then we are subtracting the number of protons. So that's how we get our number of neutrons. In this case, it would be 28. All right, so now we've got our structure. We've got 24 protons, same number of electrons because it's a neutral atom. And then mass number minus atomic number gives us our neutrons. All right, now ions, this is now different. An ion is a charged particle. So it makes sense then that your positives and negatives are no longer canceling out. So there are two types of ions. All right, now first thing is, if I think about my atomic structure, the protons and the neutrons they're going to stay. That it's not like when you make the atom, then you start changing the protons and the neutrons. You can do that with radioactivity, but we don't do that till Chem 2. The electrons outside the nucleus, those are the ones that can come and go, right? So electrons are lost, electrons are gained. It depends on where we are on the periodic table, and we'll talk about that more as we go. So first, all right, if electrons are lost, so if you have an atom that loses electrons, then that means your number of positive protons is greater than your number of negative electrons, right? Because if we go back up to chromium, we had 24 protons, 24 electrons. Well, if chromium loses electrons, it went from 24, let's say it goes down to 22 electrons, right? So now I've got still 24 protons, but I only have 22 electrons. I've lost electrons. So when you lose negative particles, you become overall a positive ion because now there's more plus than there is negative. All right. And that name of a positive ion is called a cation. All right. And what I put in here is what I think is helpful is remember that your T in cation is your plus sign. So that helps you remember that cations are positive ions. At least I thought that helps me when I was learning it. So cation, just terminology, means it's a positive ion. So then the opposite is true. If electrons are gained, then your number of electrons is greater than your number of protons. And that means you now become overall a negative ion. And the name for that is an anion, which to me always looked like it was short for a negative ion. I've never had any verification that that's actually where that comes from, but that to me is what it looks like. All right, so a negative ion, right? A negative ion is anion. So just terms, cation is positive, anion is negative. And it depends on whether the electrons have been lost or gained. So if you lose negative particles, you're going to become positive overall. If you gain negative particles, you're going to become negative overall. All right. So if we go to the next page, that's where you'll find the term the anion. Next thing we're going to do is looking at our periodic table, we're going to start to understand how can we predict whether we're losing electrons or gaining electrons, because it turns out we can have some pretty good predictions based on where the element is on the periodic table. Before we get there, though, we're going to look at specific families on the periodic table, and then we'll start talking about those changes that we predict with the electrons. All right, so the periodic table to me, fascinating. Mendeleev was a Russian chemist, scientist, and he was a professor. And at the time, mid 1800s, you can imagine, right? There's no internet. There's no real centralized location of all the information that's really been discovered at this point, which is also fascinating. I mean, they would have regional, science type, what's the word I'm looking for? Like conferences, back in the day, conferences, and everyone would kind of get together and share information of what they had at the time. So Mendeleev, he was known to not be much of a sleeper. So he would take like little 2 to 3 hour naps randomly throughout the day. And the idea behind the periodic table came up to him supposedly after he woke up from one of these naps. But what he did is he took what we knew about the 55 elements at the time. We only knew 55 of them. And he started to organize them based on their atomic mass and some also about reactivity. And then what he found was there were patterns. There was this idea, and his original periodic table is not quite like the one we have now. With more information, we made it better over the years. But like, for example, he knew based on this pattern, like he had fluorine, chlorine, bromine, iodine, and then he left a space for what he called eka-iodine, right? Like something's going to come after that. And later it was acetine. And this periodic table is a little bit outdated. Now there's tennessine. That was our most recent elements discovered. So this organization on the periodic table is actually quite brilliant. I mean, to me, the periodic table is the best cheat sheet ever made. You just have to know how to read it. Okay, so first thing is, I'm going to be over here on the right. If I look here, some element names we should know, boron and aluminum. Right between the two, I'm going to draw a line. And I'm going to make a stair step. So now between aluminum and silicon going down, I'm going to draw that line. All right, silicon, germanium, don't need to know germanium. And then down between germanium and arsenic. And then over between arsenic and antimony. Then down between antimony and tellurium. Over between tellurium and polonium. And then down between polonium and acetine. That right there is the boundary that separates metals from nonmetals. So if you look at your periodic table, most of it is whatever this is on the left, which are metals. Now the 2 rows down here at the bottom, the lanthanide series and the actinide series, they fit right in this atomic number gap that you see right on the period, like at barium 56, lutetium 71, that gap is the lanthanide series down here at the bottom. All right, so they're still on this side of the metalloid stair step. So this right here, and we'll come back to this in a minute if you need to see it, that is our boundary that separates metals from nonmetals. So on the left, which is most of your periodic table, these are your metals. And we have different names for some of those metals. If you remember alkali, transition, we'll look at all that here in just a little bit. But one thing that metals have in common is they like to lose electrons to become, remember, positive ions. And the name for that is again cations. All right, so metals lose electrons to become positive. Remember the T for the positive sign. Metals become cations. So the exception, because with chemistry, what I find out is, there's typically rules and then there's always an exception. All right, the exception here is hydrogen. And different periodic tables will put hydrogen in different places. Remember when I very first started teaching, the periodic table that they had in the room, the hydrogen was actually right in the middle. And that actually kind of made the most sense to me because it is a nonmetal, but it does form positive ions like a metal would. So it's kind of interesting, but just know hydrogen is an exception. It is not a metal. It is a nonmetal. All right. Now, hydrogen is the only exception to the left of the stair step, and that is the nonmetal. Everything else is going to be a metal. All right. Now, again, hydrogen, like metals, likes to lose electrons to become a positive ion. That's what's a little unusual about it. So when I go to the right side of the periodic table, all right, so the right side of the stair step. So we're looking at like nitrogen, oxygen, fluorine, chlorine, all of your argon, neon, noble gases. These are your nonmetals. All right, and nonmetals typically like to gain electrons to become negative anions. All right, so nonmetals like to gain electrons to become anions. All right, so as we were talking about, it turns out that for a lot of these elements, where they're placed on the periodic table helps us understand, okay, how many electrons should they lose? How many should they gain? Which way are we going? So we know that if we're on the right side of the metalloid stair step, these elements like to gain electrons. Oxygen, nitrogen, phosphorus, they like to always gain electrons when they ionize. The metals like copper, nickel, cobalt, they always want to lose electrons. So that's why these are always positive ions. And on the right, we have our negative ions. Now, why did they do that in the first place? Well, it turns out that the noble gases at the very end, the helium, neon, argon, krypton, xenon, radon, there's something about the electron structure in these noble gases that is incredibly stable. It's like as soon as you have that electron structure, a stability switch clicks on and it just becomes very stable, something about that electron structure. So these elements, for the most part, they want to end up looking like that same noble gas electron structure. Now, the nucleus is still different because, of course, it's a different atom, but the electron structure is going to end up looking like one of these noble gases. All right. And so that's going to make some of these elements, their charge that they form as an ion, it's going to make some of them easy to predict. Before we get there, though, I don't want to forget to mention when we separate metals from nonmetals, that boundary, we have elements that are kind of metallic and kind of non-metallic. And the example I always like to use, because I think it's the easiest, like that you would be aware of, is silicon. So if you do any kind of baking, or if you were in lab today using the hot hands, that was silicone. And a lot of oven mitts are made with silicone now. And it's a rubbery material. And it's interesting that it can, when you use it to transfer heat, which you can, like if you bake and all, they'll have silpats, which you line your baking sheet with, or you even have silicone bakeware now. And it's interesting because you have this like rubbery material that is transferring heat. And normally we think metals are going to transfer heat. So along the boundary here, these what are called metalloids, they can have metallic and non-metallic characteristics. There's interesting chemistry here, but there are 7. Now we only have 4 that we need to know because the name we need to know. Boron, B, right? That is a metalloid. Aluminum is a true metal. We know aluminum, right? That kind of checks all the boxes for what we think for metal. Solid at room temperature, shiny, not powdery, anything like it, just looks like a metal. I don't know how else to explain it. Good conductor of energy. Then we've got Si, which is silicon. Germanium is a metalloid, but it's not on our list to remember. So we don't really have to worry about that one too much. Arsenic, As, antimony, Sb, tellurium, we don't need to remember because the name, and the same with polonium. So basically, when you look at your metalloid stair step, it's everything that is above and below one of those stairs except for the aluminum. So those 7, those are your metalloids. All right. And again, the only ones that we specifically need to remember, because these names we need to remember, are boron, silicon, arsenic, and antimony. Those are the 4 that then we have to know those names, but like you won't be asked for germanium because it's not on your list to remember. But these are your 7. So again, metalloids, sort of metallic and non-metallic. So if we go back to thinking about ion formation, which charge would you expect? It's going to be a big question mark because it's going to depend on what it's bonded with. So here the charges are a lot harder to predict. All right, so we got our metals versus our nonmetals versus our metalloids, right? So if we kind of just keep track of where we are in the notes, that paragraph where we left off, that's what we have here. We've got our 7 metalloids, metals, and then our nonmetals. All right, then if we keep going, our main group elements. All right, so you notice on your periodic table, you've got 2 tall columns on the left and 6 tall columns on the right. Those are what are called the representative elements or the main group elements. In the middle 10, so let me grab a different colored pen really quick. I think I'm going to take my marker and highlight it. If I go down between scandium, calcium, yttrium, strontium, right down there, and we go over, and then again down right at zinc, cadmium, and mercury, right in here. those right there, those metals specifically, those are called your transition metals. And I was told that it was called a transition metal because it's where you're transitioning from metal to non-metal, but I really don't like that explanation. I want more verification on that because that seems like number one, a very long transition. And then number two, if you look just past the transition metals, you still have more metals. Aluminum, like we talked about, metal, tin, lead, bismuth, those are all metals. So I didn't like that definition of why it's called a transition metal. So, but whatever, that's what they're called. The other elements, the 6 tall columns on the right, the 2 tall columns on the left, those are your representative elements. They're not transition. We don't have to worry about the rare earth elements down at the bottom. The lanthanide series, actinide series, don't worry about the name for those. So we've got our transition metals. The other metals that we have a special name for, if we go to group 1, lithium, sodium, potassium, rubidium, cesium, francium, those are all specifically called, and I'm going to flip this and go sideways. Those are your alkali, ALKALI metals. All right, again, not hydrogen. Hydrogen at the top is a nonmetal. The family right next door, beryllium, magnesium, calcium, strontium, barium, radium, those are your alkaline earth metals. All right, so the way I always remembered those apart, because they sound so similar, is that you have group 1, group 2, right? The first group is group 1, think one name, one alkali. Group 2, think 2 names, alkaline earth. So that made it, I think, easy to keep them apart. All right, so alkali metals, trying to get it to come back. There we go. All right, alkali metals, group 1, one name, alkali. Group 2, 2 names, alkaline earth. All right. Now alkali, alkaline, line or lye. I mean, if you've heard those terms, it means base or basic. So lye, typically sodium hydroxide, extremely strong base. Alkali, alkaline. The reason for that is these metals, when they react with water, they turn the water into hydroxide, which is base. So that's why they're alkali, alkaline earth metals. All right, these are highly reactive metals. We don't find these in the earth as pure metals. They're always as compounds. They're very reactive. Okay, so on our periodic table, we've got hydrogen, nonmetal, alkali metals for the rest of the family, alkaline earth metals for group 2. Then we have all of our transition metals. When we get to the boundary of the transition metals, we have boron, which is a metalloid, and then aluminum, gallium, indium, thallium, which are metals. Then we've got carbon, which is a nonmetal, then silicon, germanium, metalloid, and then tin and lead metals. Nitrogen, phosphorus, I almost said farsnic. Nitrogen, phosphorus, nonmetals, arsenic, antimony, metalloids, bismuth, metal. So these columns get a little complicated. So we'll talk about that when we get to charges. Now, all the way at the very end, right? The electron structure everybody's looking for: helium, neon, argon, krypton, xenon, radon. These are called your noble gases. And I know students like to remember that because they're noble, you know, they stand alone kind of thing. That works. Right next to that, we've got fluorine, chlorine, bromine, iodine, astatine, the new one down here at the bottom, tennessine. These right here, that whole family, these are called halogens. HALOGENS. All right, other families have other names like the chalcogens, but those are the main ones that I want you to remember. You may see chalcogens though on your practice quiz, but fairly easy to figure out. So we've got noble gases, halogens, nonmetals, right? So they're under the broad umbrella of nonmetal, but specifically we have noble gases and we have halogens. All right, then we've got our metalloids along the stair step. So if I asked you to classify sulfur, you would just tell me nonmetal. If I ask you to classify antimony, you'd say metalloid. If I ask you to classify bromine, you would say specifically halogen. Yes, it's a nonmetal, but specifically it's a halogen. All right. So we've got all of that. Now let's talk about ions. We got our families. What's special about the family? So the elements that are in the family, this is where Mendeleev kind of started this organization and genius, is that elements in a family behave very similarly. And when we get into electron structure after exam 2, we're going to really dive deep into that. But it turns out that lithium, sodium, potassium, rubidium, cesium, and francium, they all have something in common. And that is in their shell. All right. And what I mean by that is when you have your atomic structure, we don't have this again, this is going to come later. You have your nucleus in the middle. And then outside of that, you have these shells where the electrons can live. And depending on how big the atom is, tells you how many shells are occupied. So like hydrogen is row 1, so it only has 1 occupied shell. Lithium is row 2, so now it has filled, or it's not filled, but it's used 2 shells. Sodium has used 3 shells. Anyway, that part doesn't matter. But it turns out that all of those alkali metals and hydrogen in their outermost occupied shell, all of them have something in common, and that is they only have 1 electron in that outermost shell. So what they do is when they form an ion, they lose that 1 valence electron. And when they do that, they lost a negative particle. So overall, there's a positive 1 charge because now the protons have stayed the same, but now they've lost one of those negative charges. So overall, they're left with a +1. So they lose 1 electron. The alkaline earth metals, what they have in common is that outermost shell has 2 electrons in it. And so what they like to do is they lose both of those electrons and they form positive 2 ions. So we know that as an ion, sodium will always be +1. As an ion, magnesium will always be positive 2. So the representative elements, it turns out it's usually pretty easy to predict their charge. The transition metals don't have that. They have different charges, and it's not something you can just easily get by looking at the table. Chromium, for example, likes to be either a +2, +3, or a +6. Iron, typically +2 or +3. Copper, +1 or +2. You know what I mean? It's not something that we're going to sit and try to memorize. We're just going to, we'll figure that out later. There are 2 transition metals, though, that always have the same ionic charge. Silver, Ag, number 47, is always a +1 charge, cation. Zinc is always a +2, right? And then to keep with this diagonal, if I look at my diagonal right here, aluminum is always a +3. So that makes it easy. We got 3, 2, 1, right? So aluminum is always a +3. Zinc is always a +2. Silver is always a +1. Sometimes students will get the aluminum and the silver backwards. Everybody remembers zinc is a 2 because it's in the middle. But what you could do is just remember the charges are like the alkaline earth metals, right? You go 1 and then 2 and then 3, right? So go left to right, 1, 2, and then 3 for the aluminum. All right. So the transition metals, we're not going to memorize any of the other charges, just silver +1, zinc +2. But what they all have in common is they will be positive ions. It's just the charge is going to vary. All right. There are others in there that are only 1 possible charge, but we're not going to worry about those. Like cadmium is also always a 2, but I like the diagonal. That makes it easy to remember, just 3, 2, 1. All right. If we go to the right of the metalloid stair step, remember now we're talking about nonmetals that want to gain electrons. And it goes back to that valence shell, the outermost occupied shell, and trying to look like a noble gas. So fluorine, there we go. Fluorine has 7 valence electrons. So if I look at my group numbers, right, I've got group 1, group 2. We're going to skip transition elements. This is group 3, boron. Carbon group 4, nitrogen group 5, oxygen group 6, fluorine group 7, and halogens technically are group 8. So they have fluorine, chlorine, bromine. They all have 7 electrons in their outermost shell. They really want to get to 8, right? Because that's the noble gas structure. So halogens will always pick up 1 electron to become a -1 anion. The oxygen family, they all have 6 valence electrons. So they want to pick up 2 to get to the noble gas structure of 8. So oxygen family, we predict -2. Nitrogen family, you can see the pattern is going to be -3. The carbon family, I don't like putting a charge on because like we just looked at, carbon would be -4. Silicon and germanium, metalloids, not really sure what the charge would be, if it's always the same even. And then tin and lead are metals, so these are positive. So I find that I don't really like putting a charge up here. And then for the nitrogen family, nitrogen, phosphorus, and a lot of times arsenic will be -3, but bismuth would be positive, but we don't use bismuth too terribly much. All right, but just know down here at the bottom, bismuth, tin, lead, right? Those are metals. So they would be positive rather than negative. Sorry about my camera. I don't know why it's doing that today. All right. So back at where we were in the notes. Example question says, how many electrons will be present in the ions of sodium, magnesium, nitrogen, oxygen, and fluorine? So first, let's look at sodium. All right. So sodium, I'm going to do this sort of the long way. For each of these, we're going to look at protons and electrons. All right, so sodium, going over to my periodic table, has 11 protons. Now, since we're looking at the ion, what I know about sodium is as an ion, it will be a +1 charge, cation, which again means it's lost an electron. So instead of having 11 electrons in the atom, it only has 10 in the ion, right? So you can see how a +11 and a -10 overall gets you to a +1. Then if I go right next to that and I look at magnesium, magnesium is atomic number 12. So it has 12 protons in the nucleus. But the ion of magnesium should carry a +2 charge. All right, so if it's lost 2 electrons now, we're going to have 10 electrons. All right, next we're looking at nitrogen, oxygen, and fluorine. And so these are going to be on the other side of the table. Nitrogen is atomic number 7, and we expect a -3 charge. So we know it has 7 protons because that's the atomic number. If it's a -3 charge, that means it's picked up 3 electrons. So 7 + 3 gets me to 10. All right, if I go and look at oxygen real quick, oxygen is atomic number 8 with a charge of -2. So it has 8 protons in the nucleus. Charge of -2 means it's picked up 2 negative particles. So it has 10 electrons. And I think you can see what's going to happen with fluorine. Fluorine is atomic number 9. It would carry a -1 charge. So again, we're getting to that total number of 10 electrons. So what we notice about these 5 ions are called isoelectronic. And iso, again, meaning the same. So iso means the same. And electronic means it has the same number of electrons, the same electron structure. And when I look at that, remember we talked about the whole reason to form these ions is to end up feeling like a noble gas. So when I look at my periodic table, there is a noble gas that has 10 electrons. It has 10 protons, 10 electrons. It's incredibly stable, and that is neon. So fluorine wants to look like neon, oxygen like neon, nitrogen like neon. The nonmetals, that outermost shell, the valence shell, is almost full. So they just want to go ahead and fill it. But the metals, their outermost shell is almost empty. So instead, they release, they dump, they get rid of electrons. So sodium and magnesium, they release electrons to go back to look like a stable neon core. So all of these ions are isoelectronic with neon, right? The noble gas neon. All right, and again, with the representative elements, for the most part, that is the whole point, is to get the electron configuration of a noble gas. So fluorine, like we saw here, wants to end up looking like neon. If I go back to my table, chlorine is going to want to look like argon. Bromine is going to want to look like krypton. And iodine will pick up an electron to look like xenon. All right. Okay. So last page of the notes, we were talking about how that mass number on the periodic table is not a whole number. We actually learn in this class how those numbers are determined. And we talked about them being a weighted average. So that is what's going to happen on the next page. So it says here we've got these isotopes of copper, right? Cu from cuprum. And the two naturally occurring isotopes, copper 63 and copper 65. It's not a 50-50 abundance, because if it was, the mass number would be 64, right? If I have half of it is copper 63 and half of it is copper 65, it'd be an easy average. The mass number would be 64. So the weighted average is because the copper 63 is 69% abundant, so it's the majority. And then the copper 65 is about 30%, so there's less of that. So when you do a weighted average, you take the mass of that isotope, which is given to you here. AMU is atomic mass units, all right? So that's what's here. And you multiply it by the percentage, but now converted to the decimal, right? So 69.17% means parts per 100. All right. And so then that is 0.6917. So question came in. This is a good question too, with the ion charges. Sorry about that. About whether or not it matters if the plus or minus is either before the number or after. And what that means is, like, nitrogen, would it matter if I write it as 3 minus 3 or 3 minus? And to me, the answer is no. I always do -3, but if you do 3 negative, it's the same thing. So you can write that either way. Like I said, I like -3, but that's just personal preference. If you write 3 negative, works just as well. All right, so we took our atomic mass of that isotope, copper 63, and then the percentage of that in abundance converted to the decimal form. And then we take our other isotope atomic mass, the 64.9278, and multiply by that percentage, but now converted to the decimal. So 30.83% is 0.3083. When I take that atomic mass times the percentage in decimal form, I get a value. When I do the same thing with the second isotope mass times the percentage in decimal form, I get a value. Now I add those two together, and that's my weighted average. So remember how we were talking about the copper 63 is much more abundant than the copper 65. So we knew that the atomic mass was going to be closer to 63 than 65. And that's what we see here, right? So we've got more of copper 63 than we do of copper 65. So that's how we do a weighted average, right? Weighted, because it's not just 50-50. Then we could just add them together and divide by 2. This is why we have to do this math, right? Now, when I start doing mass, mole, molecule calculations, and I use those atomic masses from the periodic table, I typically round to 2 decimal places. So you can take 63.5453 to do your calculations. I just feel like it's more than what we really need. So I go to the second decimal place and round appropriately. So 63.545, since I'm cutting off the 5, that 4 would round up to a 5. All right. Now, this is what I had mentioned in the Tro book, how I thought it was a little strange. I'm going to introduce this really quick, and then we're going to take a break. We start getting into what a mole is, what is the mass of a mole, how many particles are in a mole. And he introduces everything to do with atoms in chapter 2, and then everything to do with molecules in chapter 3, but it's the same. It's the same thing. It's just we're looking at an atom or molecule. So that's why I think it's better to just put them together. Especially if I'm going to quiz you on mass, moles, molecules, I don't want to have 2 separate quizzes for elements and compounds. It's just one quiz because it's the same topic. So these conversions we're going to remember when we get back from the break, because we're going to look at that again. But this question here really quick. All right, copper. You're probably familiar with this. When we have a penny, the inside of the penny is not copper, because copper is way too expensive. The cost of the penny would be more than a penny. The inside of the copper is actually a zinc disc. And then outside of that is the copper coating. So it says here, if we know that the penny is actually only 2.5% copper, the rest of it's zinc. Knowing that the mass of the penny is 2.500 grams, what is the mass of copper in the penny? So if we know that 2.500 grams is the mass of the entire penny, And then like we were talking about with the weighted average, I know that 2.5 parts of the penny is copper out of 100 parts, which is the whole penny, right? That's all a percentage is. Percentage means parts per 100. So if I have 100 parts or 100 grams of the penny, only 2.5 grams of that is copper. So that's the percentage. The other way students will do this is 2.5 divided by 100 is the same as 0.025. So also what you could do is take the 2.550 grams and multiply it by 0.025. Either way, you get the same answer. Just depends on how your math teacher taught you the percentages. So percent to decimal form, just divide it by 100, or take it, divide it by 100. Either way, it's the same idea. So 2.5 times 0.025, and I'm going to go ahead and keep the 4 sig figs here. I have 0.0625. Technically, there'd be another 0 there. Let's not worry about sig figs. This would be our mass of copper here. 0.0625. All right, that is our mass of copper. Now the question is, how many atoms would be in every penny? So in order to know atoms and grams, we need to know that when we look at our periodic table, that mass number that we have for copper, right? 63.55. It's a mass number. So we think the unit is probably grams because that's our standard unit for mass. But an atom of copper is so small, it wouldn't weigh 63 grams. Like 63 grams is something you could see. You could put that on the scale and measure that. So an atom of copper is not anything we can see. So what is 63.55 grams? It is the mass of 1 mole of copper. So then the question is, well, what is a mole? A mole is a representation of 6.022 times 10 to the 23rd particles. Now the particle type is going to depend, and this is where Tro makes the distinction between chapter 2 and chapter 3. If we're talking about an element like copper, then we're talking about atoms of copper. All right. If we're talking about a compound like water, then we're talking about molecules. And you remember that from Tuesday's lecture, just terminology. So if I have 0.0625 grams of copper, if I want to figure out my number of atoms, what I know is when I look at my periodic table, I know grams is going to go on the bottom to cancel out. My conversion is 63.546 or 63.55, depending on if you want to round. That is the mass of copper for 1 mole of copper. But I want to know how many atoms. So 1 mole is 6.022 times 10 to the 23rd atoms. And again, atoms because it's an element. So these are equivalent statements. So for any element or compound, 1 mole is equal to 6.022 times 10 to the 23rd particles. And that is equal to what's called the molar mass from the periodic table. And that is for copper, that is what we were calling a mass number. I'm now going to refer to it as a molar mass because it is the mass of 1 mole of copper. So copper, molar mass, 63.546. Cadmium, molar mass, 112.411. Now, same number of particles, 6.022 times 10 to the 23rd. The cadmium is heavier because there's more protons and neutrons, right? So that goes back to the atomic structure. So the 1 mole of cadmium weighs more because there's more subatomic particles. So on my calculator, I like that EE key. We were looking at this on Tuesday. So if I take my 0.0625, that was our mass of copper in the penny, right? And then I'm going to multiply that by 6.022. Instead of times 10, I hit the EE key, 23. All right. And then I'm going to divide that by 63.546 because it's in the denominator. So I have 5.923 times 10 to the 20 atoms of copper in a single penny. All right. So really quick, I'm going to type it in before we take the break. We're going to take 0.0625. Multiply 6.022 EE 23 All right, so don't hit times 10, just hit EE. Then divide by 63.546, and you get your 5.923 rounding up times 10 to the 20. There's your exponent. Now, my TI calculator has the EE key. Sometimes you'll see something written as an EXP key, and then sometimes you have to be a little bit careful here because you can have the EE key, you can have the EXP, or you can have times 10 to the X key, but not 10 to the X, right? Because when you look, 10 to the X is the inverse of log. So that's not, we don't want that. So it depends on your calculator. I've got the EE key. I have another calculator in my office that's got the EXP key. And some calculators I've noticed have a times 10 to the X key. But again, not 10 to the X because that's the inverse of log. Okay, so sorry I went a little bit over. I'm going to break here really quick. We're going to come back in the other Zoom room at 12:30, and we're going to do this last question, but I want to make sure you get somewhat of a break.